Hello, everyone. My name is Robert Steller. I'm from Germany, but I am living in Canada since about 20 years. And I am a certified building biologist and an electromagnetic radiation specialist. And also, we're going to talk about the whole subject of building biology in regards to electromagnetic radiation. As I said, I live in Canada now. Since 20 years. I left Germany and I started a business here in Canada about building biology, which basically is the protection of human beings from any kind of natural and man-made threats we may come across. And of course, the name building biology goes together with a building. So that's why we call it that way. We live in buildings and we work in buildings. And then we have a built environment, let's say a big city or a small village. So humans have built something. So when we go really, really back in human history, humans always tried to protect themselves from any kind of threats. So let's say when there was a big thunderstorm thousands of years ago, people ran into a cave to not get hit by lightning. Or they built little straw roofs to not get sunburned, because the electromagnetic radiation from the sun can be very strong, and that can be influencing human health as well. So there's natural radiation, and there's also man-made radiation. Now, building biology as a science deals in both ways, but primarily in the radiation part, which has been created by humans. So when we go back approximately 100 some years, humans started to make electricity, and they experimented with electricity. So Thomas Edison, one of those people, Marconi, another person. Marconi tried to send electromagnetic radiation through the air as radio waves, and so that's where it started. Over the last course of the 100 years, things got more sophisticated, and then we had all of a sudden lights, electric lights in our houses. We had streetcars, railways. So there's a lot of electricity has been developed, and a lot of things and equipment has been developed, and people thought it would make human life easier, which it did. So there's an electric machine that does something for you. Let's say making bread. You throw everything in this big bowl, and the electric machine makes the dough, and then you can make the bread. So there's a lot of tons of things. In the modern days, of course, in the computer age and in the digital age, we have much more sophisticated machines, but they're still machines. We have to tell them what to do. Anyway, as far as building biology and the exposure to those electricity fields is concerned, that's where building biology comes in. So I'm going to break it down a little bit into the different fields, because the word electromagnetic field is really not a scientific term or a term in physics, because it's a combination of things. So EMF, electromagnetic field. I break it down into the electric field and the magnetic field. So let's say electricity is made, and a few years ago we were taken to the Iguazu down there, and there was a big power plant in Brazil. Fascinating, very fascinating. So that's where they make electricity, for example. And then they send the electricity to people. In order to get the electricity from the plant into your house, so you can turn the light on and plug your mixer in or whatever you may have, your computer, it has to be sent. The best way of sending electricity in modern days is through wires. And in Canada, we almost exclusively now use aluminum wires for the big tension lines. So the electricity goes from A to B. And on the way from A to B, let's say from the Iguazu Falls and over to Sao Paulo or Curitiba, it runs through these wires, and everybody knows these big tension lines. And there is a big field around those lines. But there's also fields around anything electric. So if you use a hairdryer, there's a field around it. If you watch TV, if the electricity comes into your house, the wire from the street going onto your house, or it comes underground. So we're surrounded by electricity, and that can be a danger factor if we don't know where the electricity is. So let's break it down, the electromagnetic field. I'm just looking here at my PowerPoint. We said several components to this. Basically, it is the AC electric field, which is alternating current, man-made. It reverses its direction 50 times per second or 60 times per second, depending where you live. Then there is the AC magnetic field. Then there is the DC electric field, also widely known as static electricity or even air electricity. Then there is the DC magnetic field, or we call it magnetostatic. The simplest field is from a real magnet, which we all know. You stick it somewhere on a magnetic board. But there's all kinds of magnets. Let's say a speaker from a radio has magnets in it. A telephone receiver has a little magnet in it. And the biggest magnetic field, DC magnetic field, is the Earth itself. And that can be a problem if that field gets distorted. And of course, all these things we talk about is under the big umbrella building biology, because the Earth magnetic field is a very natural thing. We humans are used to it. But if for some reason that natural field from the Earth gets distorted, then it would be hitting the human body in a different way.
It's 5 o'clock.
So if you walk around on the ground, let's say in the Amazon jungle, you get a natural field. There's nothing distorting that field. If you live in a house with a lot of steel in it, that Earth field may, or will, not may, will get distorted and would hit the human body on an angle. So let's go further. The fifth component of EMF is the electromagnetic wave, or also known as radio waves. The simplest radio wave 100 years ago went from an antenna through the air, and in another area there was another antenna, and it went into resonance with that field, and then you could hear music or human voice. These were the early days of radio frequencies. In our days, that also consists of microwaves. The most known microwave is microwave oven. You put something in and it heats up. But microwaves are also used in many, many, many different ways. And we'll talk about that as well. The last component of EMF is radioactivity. And again, the Earth is a radioactive planet. It's a very natural thing, but it is not as strong as human-made radioactivity. A widely known human-made radioactivity source is X-ray in medicine. So they shoot the radioactivity through the body and then they get an image. Nuclear power plants. There's other areas of radioactivity. For example, in the smoke alarms in houses to detect fires, there's a little tiny bit of radioactivity, and it's a little crystal that is radioactive. Not dangerous for humans, but we had cases where the thing fell down and the baby was crawling on the floor and ate the little crystal. Now it had a radioactive crystal inside the baby's stomach, and it had to be removed with an operation because that wouldn't be good. But other than that, it's not really dangerous. So radioactivity. For example, the old TVs, the big boxes, they had a cathode ray tube, and that emitted radioactivity. Radioactivity can also be found in building materials. Again, now we're talking about building biology again. A granite countertop or a pumice wall. Somebody builds a house with radioactive stone, and the bed is close on the wall, and you would get elevated radioactivity during the sleep. So that's where building biology comes into play as well. We actually test for building materials and radioactivity because we don't want it too close to the human body. So these are the 7 different things. I repeat that. AC, electric field. AC, magnetic field. DC, electric field, electrostatic. DC, magnetic field. Electromagnetic waves or microwaves, and radioactivity. These are the 7 basic components. So we said already that the electricity comes through the big power lines. Every country has them. That's the distribution part. You don't want to live too close to one of those power lines. Everybody would say, yeah, if you have a house and it's too close to that, you would say, maybe not a good idea. But we would know that. We would see it. A lot of the electric field we don't see. So therefore, we need to measure it. How do we measure the electric field? There's a few ways. I show you during the lecture a few instruments. So this, for example, is a combination instrument. It measures electric and magnetic field, as well as this. And then there's also a kit called the body voltage kit. The electric field has the ability to go onto a human body. It's called, in technical terms, it's called capacitive body coupling. We call it body voltage. And you can measure that body voltage. If the body voltage is high, you are getting exposure from the electric field, not the magnetic. We talk about that in a few minutes. The electric field couples onto your body, stays there as long as you're in the field, and influences processes in the human body. That's where we look in building biology. How does it influence the human body? Well, it can make you very sick. Over time, if you sleep in a high electric field environment. The best way to find out is measuring it. So there are some inexpensive instruments we can use to find out what is my exposure. And then maybe sometimes moving the bed into another area of the room can help. So that's the electric field. Of course, the other thing with the electric field is we all live in an electrified environment. And therefore, we all get a certain amount of electric field exposure. Especially at night, we want to reduce that. During the day, we can't do much about it. If you work in a factory and you're standing on a machine which uses electricity, or you work in an office and you work on a computer, we're surrounded by electricity. During the night, that should be minimized. So let's go further and go to, well, remediating the electric field, ideally in your bedroom at night, turning it off. As long as there's not an exterior source, your house is too close to a power line, we can't turn that off. But if it's not, turning your bedroom off would be one of the remediation strategies. Grounding things can help, but with grounding, one has to be careful and one has to really know what to do. So next thing is the magnetic field. So the magnetic field is also always present when they send electricity to somewhere from the power plant. So there's a magnetic field, and of course the electric field is already there. Now the magnetic field moves in and says, it's a nice place, I want to be here too. So, and then the magnetic field is there too. And there's always a field around those power lines. But there's also a magnetic field around every equipment which uses electricity. Hair blower, for example. You blow your hair, that creates a magnetic field, plus the electric field. Always remember, electric field is always there. If you stop using the blow dryer and you would hold it in your hand, you still get the electric field from the cable, but the magnetic field has stopped. Same thing with the fridge. There's a magnetic field around the fridge. If you move out away from the fridge, the magnetic field stops at some point. So the big difference between a magnetic field and an electric field is the magnetic field has an end. If you go away, no magnetic field. The electric field stays and, let's say, jumps onto your body. That's a big difference. That's why the electric field is much more difficult to remediate. Okay, so we said that the magnetic field is always present when something runs. So if you live too close to a power line or electrical wires, there will be a magnetic field. Again, in order to find out how big that field is, we need to measure. Again, one of those, or this is a little more sophisticated, but this will do to show you, am I exposed to a magnetic field or not? Or how far do I have to go away from a magnetic field? In Toronto, somebody wants to buy a house. They call me, there's a power line, the house is here. Can I buy that house? I don't know. I have to go and I measure. And if the house is outside of the magnetic field, okay, you're not exposed to the magnetic field. That's how it works. So here we go. Again, the measuring part is important. Now, if we look inside buildings, we are surrounded by electric and magnetic fields. And there's many, many sources, as you can imagine. If you go inside a house, from turning the light on when you come home to turning the TV on, washing machine, all kinds of sources. So identifying, sometimes we don't know the sources are there. In an apartment building, the neighboring fridge is right behind your bed, but you don't know that. If you measure, well, then you put your bed on the other side. Now we're going to, let me check here, DC fields. DC electric field. The main DC electric field is constant thunderstorms on the Earth, creating a certain amount of air electricity. Now that is a normal thing, but some people, electrosensitive people, they would feel that. For building biology purposes, we want to look at exposures to the human body. For example, you have a synthetic bed covering and you turn at night and you rub that and you have a plastic pajama on, you would constantly create a DC electric field, electrostatic. So natural materials, for example, would be the answer to that. And again, it can be measured, but it's a little more complicated to measure those things. Then the DC magnetic field. The DC magnetic field, or earth magnetism, is a problem in buildings with steel reinforcement. Any form of steel will deter or bend the magnetic field. And that can be a problem. Again, it needs to be measured and see if you are exposed to a distortion of the DC magnetic field. Okay, we have to move on. And a simple way to measure the magnetic field is a very good compass. Like you go into nature and you're hiking and you have a compass. So a liquid filled compass would be a good instrument to have. You can slide that over your bed. If the compass moves, the bed is magnetic. And then you may get a different mattress. The coil mattresses, they are always a problem. They're magnetic, or metal bed frames, things like that.
It's so 5:15.
A simple compass would be a good instrument to measure that. So now we're going to go to the high frequency. High frequency or radio waves. So that's huge. Like 100 years ago, high frequency was, well, very little, and not complicated waveforms. It was just a radio wave going through the air, and that was it. Today, we have many, many complicated waveforms to make all these things happen. So you have an iPhone or a cell phone. You can watch TV while you walk on the street. To make that happen, they had to make or create extremely difficult waveforms. So they're taking the microwaves, breaking it apart, making it sophisticated, and then sending it out through the air. The latest thing people talk about is 5G. So 5G is a whole different, separate issue and technology, but the basic things with high frequency is we're surrounded by it, unless literally you're in the Amazon jungle. And even in certain areas where people are populated, they put antennas there in order to get them communication. So we are surrounded by it. Again, we have to measure how big is the exposure to where I am. And that is very complicated. Almost impossible for a layperson to do all this measuring. It takes many years to be educated to do that. So that's why we came up with a simplified version. And I want to show you an instrument we came up with. And that measures, this instrument measures from 200 megahertz to 8 gigahertz. So the entire range of microwave exposure. Now, obviously, there are some waveforms which are very complicated, and an instrument like that could not measure it. But the good news is that this instrument can detect all those major fields and microwave exposures we get. And that's a very good thing. I'm going to turn it on for a second. Now, let's see. So there's not much going on here. It shows you how many microwatts and what the source is. And you can, so I'm sitting in my office. I'm getting very little Wi-Fi from my neighbor. Nothing from my computers because they're all in airplane mode. But it gives you a good sense of what's going on around you. Especially, let's say you want to buy a house or move into an apartment. You can go with this instrument and see what is your exposure. If it's too high, you may not want that apartment or buy that house. So it's a very good way of finding out what is the exposure, what is going on. And of course, then with all fields, we always want to know what can we do about it. Well, the system is there. We are being exposed to. The only thing in the modern world we can do is like the people running into the cave thousands of years ago. They didn't want to get hit by lightning. They went into the cave and the lightning did not go there. They were safe. In a similar way, we could go in a cave, but nobody wants to live in a cave anymore. So we take the cave technology. The cave is a hole in a big rock or mountain, and there's protection. For modern fields, and we're surrounded by it, shielding would be one of the main things we can do to protect ourselves. Very simple example, in a bedroom at night, you're exposed to microwaves from surrounding towers. Hold on. From surrounding towers. We have to shield ourselves. So, for example, in Canada, we have bed canopies made out of shielding fabric. And the shielding fabric bounces the microwaves off. Works only at night, but when you're sleeping, you do not want to be exposed too much. So the body goes into a different mode during the sleep. So in that regard, that would be one thing many people can do. And sometimes that's the only thing you can do. If you're in a house, you can shield the walls, perhaps. If you design a house, or if you build a house, then you can build it in a way that the building, the house itself, becomes a cave. A nice, expensive cave, of course, but it could be the cave idea of shielding you, blocking you. Now, I'm always tell people, if they build a new house, you want to use materials which naturally shield already from microwaves. So a wall makeup. So when I built my own house, it's very thick walls, and the radiation dies inside the wall. It doesn't reach the inside. That's the idea, similar to the cave. So that's pretty much as far as electromagnetic exposure is concerned. A little bit to personal behavior. Obviously, if you use your cell phone for 8 hours a day, you're being exposed for 8 hours a day. If you are exposed to an electric field, but you know the source may be sitting further away from your computer. So personal behavior and habits is a big issue in our modern world. I have a lot of clients, they want me to fix their exposure problem. And they're surrounded by tablets, wireless computers, Wi-Fi, then they're on a cell phone. Well, either you smoke or you don't smoke. Either you use your cell phone excessively, with a certain risk involved, of course, or you lower the usage of your exposure. So in many regards, we personally can decide, I don't have Wi-Fi. Look, I'm talking to you in Brazil without Wi-Fi. How is that possible? Well, we record it, but I don't have Wi-Fi. I'm connected to the world without Wi-Fi. Wi-Fi is one of the, I would say, if you talk to me about the Wi-Fi versus 5G, I would say that Wi-Fi is a bigger threat to humans than 5G. Because Wi-Fi is in your house. 5G might be out there. We may be able to easily shield it, keep it outside. If you have a Wi-Fi router in your house, well, it's in your house. So, but it's your choice. And trust me, as far as connectivity is concerned, you don't need Wi-Fi. It's totally possible without it. So what I'm saying is, we are responsible for our own exposure as far as things are concerned, like computers, cell phones, tablets, and those things. And the other issue is, how can we deal with the fields coming from the outside? There's no point in shielding your bed if you have your cell phone next on the pillow. That wouldn't make sense. So we see there's a lot we can do, from the point where we choose to live, or live in the future, or looking for a house or an apartment. So pre-screening, there can be a lot can be done to find out where's a better area with less exposure. And then obviously shielding will be always a necessity. But if you're in a better area with lesser radiation to begin with, the less shielding you have to do, because shielding is not the complete solution. So there's other things involved as well. Okay, so I think we are on almost 30 minutes, and I hope this helped. The medical issues, I have a whole presentation on the medical issues. Being exposed to electricity in any form will have an influence on our body, on the functioning of our body, and on our health. And medicine has shown that. It's proven. People don't want to believe it, but it's a different story. If you smoke and you believe smoking is not dangerous, then you have no problem, except for lung cancer 20 years later. So there is always a risk involved. The first thing is, do I want the risk? We all have to accept certain risks with electromagnetic radiation. There's no way around that. And a lot of things are up to us. And so I would say, to conclude, we talked about the different fields, and we can distinguish them. And the nice thing is we can measure them, and we can find out how big is the threat coming to me. And then you can act accordingly. If you are living in a place where you are completely bombarded, maybe you can choose to move to another place. But by being able to measure all these things brings us into a really advantageous position, and we find out how big is the threat. So, my dear friends from Brazil, I wait for the time when I can go back there and talk to you personally, and hopefully we will have a few good seminars, and I can show you in practice how to measure and how to deal with these things. And until such time, we'll do what we do now. And thank goodness for electricity and computers, which has enabled us to do that. So this brings me to the end of my lecture, and we going back to Ormi.